Hi everyone. It looks like we'll be spending a lot of summer with the Raymarching series because I'm back with a new episode, the number 9 already. This time I like to take a look at calculating and rendering light reflections, which can be useful if we want to use reflective materials. So let's get to it. I know I keep repeating myself, and for those who have been following this series from the beginning, the same introduction might be a bit boring. Still, I'd rather say it one more time. So we are building on the shader we ended up with at the end of the previous part. I have it open in front of me, and if you've been following the entire series up to this point, your code should be in the same state. If not, there is of course the option to get all stages of this project from the Godot shader pack, which you can find on my Gumroad profile and which I've linked to in the description of this video. So the introduction is behind us, and now let's take a look at how we can improve our algorithm to render light reflections on materials that we set up this way. It's clear that every material reflects light differently, and there is a certain difference between metals and non-metals. So we'll add new properties to our material structure, reflectivity and metallic. So let's expand the shader editor, scroll up where I have the structure material definition right here. And as I said, I will add two new properties, float, reflectivity, and float metallic. Okay. Of course, this is a simplified model, and especially in the case of metallic, it's not an exact equivalent of the property with the same name that we can find in the standard material 3D structure in Godot. Alright, so now the shader won't compile because we've changed the material structure, which we use in several places, so we'll need to fix that. Luckily, it's not too much work. First, I'll fix the difference function. Let's scroll down and here it is. So we need to add new properties. B reflectivity and B metallic. Very well, so this line is fine. And now in all material definitions, we'll add two new zero values at the end. Later, we'll modify them for selected models, but for now, we can treat this as default settings. So where is it? Here. We need to add, as I said, 0 and 0. Let's copy that and paste to the end of all material definitions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That should be it. Okay. So the shader can be compiled again. Let's take a look at the scene. Yeah, everything seems to be correct. Very well. Now we need to calculate the light reflection, which we'll do the same way as a regular rendering using the Raymarch function. Here it is. However, we cannot call this function recursively from within itself. I mean, after getting the color, it would be great to call Raymarch again to find a reflection, but we cannot do it right here. So we have to do it inside the fragment function over here. It will look like this. So after vec color is Raymarch RORD. Let's do the same. Copy, paste, and call it reflection. Very well. And finally, we will add this reflection to our color. So color is increased by reflection. Okay, let's take a look at the scene. Very well. Of course, nothing has changed except the entire image got brighter because the values RO and RD, which we use here as a parameters, these values remain the same inside this fragment function. I'll come back to that, and of course we'll solve this problem. But first, we need to figure out what the vectors RO and RD should look like for the reflected light. It's not that difficult because GLSL includes the reflect function, which handles the necessary calculation for us. And as you might remember, we already used that in the Phong model right here when we calculate the specular angle using the reflex function again. So let's do it in the Raymarch function. For the ray origin RO, we'll use the same principle as for shadow calculation, which I explained in one of the early episodes of this series. It's right here at the get shadow, and we can see that the point P, the point of intersection, is increased by the normal vector multiplied by the shadow dist parameter, which is actually a very small number. So let's do it right here in the Raymarch function. Okay, so after getting the color, I will do this. RO is P plus normal times shadow dist. Okay, so this is the RO. And for the direction, meaning the vector RD, GLSL and the reflect function will help us, as I just said, with parameters RD, the original direction, and the normal vector at the intersection point, like this. RD is a reflect of RD and normal vector. Okay. We still don't see any changes because, as I mentioned, the modifications to the RO and RD vectors inside the Raymarch function don't affect them outside the function. So we need to use so-called pass-by reference. So we'll add the keyword inout, the modifier inout, to the function's input parameters. So right here, inout, RO, and inout. Okay, and now, yeah, finally, we can see the reflections. Let's just expand this window a little bit. Okay, let's just zoom out so we can see them better. They are clearly visible, for example, down to the ground, where all reflections are mirrored, and or on the sphere right here, where we can see the other slightly distorted objects. And I think we should stop the camera again because it would give us a better control over zooming in and focusing on certain areas. So where was it? RO, yeah. This one, let's replace by camera. Okay, now if I can zoom in the sphere, we can clearly see all the objects that are reflected and distorted on the spherical surface. Very well. Okay, however, we are not using the new reflectivity and metallic parameters yet, so all surfaces actually reflect light in the same way. Let's improve that. First, we'll use the reflectivity property, which will have values from 0 to 1, where 0 means no reflectivity and 1 means maximum reflectivity. However, since we're adding the reflected light to the scene inside the fragment function, right here, we also need to know the reflexivity value inside the fragment function in this code part. So we'll add it as the third argument of the Raymarch function, like this. And inout float, and let's call it ref to make it shorter. And now we need to fix the calls to this function, of course. So let's create the variable float. Ref starts at 0, and let's add it here. Ref and ref. Well, and now we can use the updated ref value to multiply the reflected light. So it would be here, ref times Raymarch. It's important to use it before calling the second Raymarch because, as we know, the ref value would be changed inside because it is again an in-out parameter. Okay, let's take a look. And of course, the reflections have completely disappeared because we are setting ref to 0 right here. And we are not modifying it yet. So let's fix it right away in the Raymarch function. And I'll simply add this line. Ref is material dot reflectivity. Very well, let's take a look. Okay, still no change, which makes sense because all material have reflectivity set to 0. So let's change it to, for example, 0.2 for the ground. I'm scrolling up to the ground definition, and I think it was this parameter, 0.2, and take a look. Yeah, excellent. Everything reflects beautifully and only on the ground. The other materials remained unaffected. In addition, the reflectivity is less noticeable because we set it to 0.2, which is basically 1/5 of the maximum value. Now we can set the sphere, this one, to maximum reflectivity, meaning 1. Let's find it. I think it's sphere 3, and I will set it to 1. Wait for it. And yeah, it reflects now and has the maximum reflectivity. We can change the, for example, warp parameter of this cuboid and observe how the reflection of the distorted cuboid changes inside the sphere. Or maybe if I put the sphere closer, for the time being, -4 for the x coordinate. Yeah, maybe -3.5 to make it even closer. Yeah, now we'll observe it better, and let's find the parameter. Here it is, warp. See how am I warping the cuboid, and the reflection perfectly reflects it. Great. Okay, so I think we can put it back farther from the cuboid. Very well. So we've covered reflectivity, and now it's time to use metallic parameter. We know that with non-metallic materials, it's often true that the smaller the angle of incidence, the more light gets reflected from the surface. In other words, when our ray is perpendicular to the surface of such material, the reflectivity is minimal, and when it's parallel to the surface, as parallel as possible, the reflectivity is maximal. For this calculation, we'll use the dot product again, so we'll write this line of code. I think I'll find the Raymarch function again here, and I put it before the RO recalculation. Yeah, so in here, and let's call it Fresnel. Is dot normal and negative RD because we are looking in the opposite direction. So why is this? It's named after the French physicist Augustin-Jean Fresnel, whose discoveries in the field of wave optics are related to this principle of light reflectivity. By the way, I used the same principle a long time ago to highlight the edges of 3D objects based precisely on the same dot product calculation. Alright, but we primarily want to apply the principle to materials with a low metallic value, so we'll adjust our formula so that the result is 0 when metallic is 1 and the maximal when metallic is 0. Okay, so we need to multiply this by simply 1 minus material dot metallic. Okay, and based on that, we can recalculate the final intensity of the reflected light. So ref is material reflectivity times 1 minus Fresnel. Alright, and since metallic is currently 0 everywhere, let's set it to 1 for our sphere. Sphere. Yeah, here, sphere 3, and so I'll set metallic to 1. Okay. Alright, and now we can verify the result. So let's find the camera coordinates right here, and I will change the y coordinate. So now we rotate it, and we can see that we're looking almost directly down the ground. Light reflections practically disappear, and on the contrary, they appear at the maximum intensity when the camera is positioned parallel to the surface. Okay, I think, yeah, it is definitely there, but it might be even better if I change the reflectivity of the ground to some higher number, for instance, 0.8. Okay, now it's better reflected, and let's try it again. I'm changing the y coordinate, and the reflection is slowly disappearing. And when coming back, it will be much more visible. Yeah, perfect. Very well. Notice that the sphere is not affected by the camera's tilt at all because its metallic value is set to 1, the maximum. By the way, you may be wondering why the sphere still displays its texture on the top instead of some kind of reflections. That's because our sky is actually black. We can take a look by tilting the camera. Is black, and we know that the black color is simply a 0, so adding a black color has absolutely no effect on the final color. But let's just temporarily change it. I will disable the reflectivity of the ground in the for the default color at the Raymarch function, which is currently 0. This is the Raymarch function at the end. So let's make it some kind of shade of blue. For example, 0.2, 0.6. We'll see. Okay, let's display the. Yeah, now we can see it. First, I'll show the sky. It is light blue right now, and it is perfectly reflected on the sphere. So yeah, this is what happens if we actually use some real background. For example, if we had a skybox or a cube map, it would be reflected in our reflection materials as well. I think I'll get back to the original black and re-enable the reflectivity of the ground. Perfect. Once again, thank you very much for watching and for every like, subscribe or comment. As always, we've only covered the basic principles because there are still areas we can explore further. For example, using multiple reflections and bounces, which would make the scene even more realistic, but at the cost of higher GPU demands. Anyway, I believe this tutorial could be interesting to anyone curious about the Raymarching topic. So, take care, good luck with your projects, and I'll see you in the next video.